The main regulator spool and the components of the modulator system are part of the transmission control valve assembly. Oil comes in from the charging pump at the right side of the valve assembly. It moves the main regulator spool back against the 30 psi spring and opens the passage to the torque converter. After flowing through the converter, oil returns through an internal passage to the converter regulator spool, where converter outlet pressure is controlled. Pressure of the converter return oil causes the converter regulator spool to move to the right and to direct the oil to the cooler. Oil flows through an external hose to the cooler and then returns to the lower part of the control valve assembly. From the control valve, the oil flows to the transmission clutch pack shafts to cool and lube the assemblies before draining to the reservoir. The directional control spool is shown at the top of the valve. It is positioned in neutral. System pressure oil is available at the directional spool. If the spool is shifted to the left, fill oil would be directed to the forward clutch pack. A shift to the right would send fill oil to the reverse clutch pack. The directional spool must be in the neutral position before the engine can be started. As seen in the illustration, the plunger on the neutral start switch will detent to close the cranking circuit only when the spool is in the neutral position. The range spool is shown at the bottom of the valve. It is shown in the first speed position, and oil has already filled the clutch pack. The springs behind the modulator piston are at full compression. The transmission control valve assembly also contains a disconnect circuit. The disconnect circuit consists of the solenoid valve mounted externally on the right side of the control valve and the neutralizer spool located in a bore of the transmission control valve. The illustration shows a cutaway view of the solenoid valve. It is shown separated from the control valve and rotated 90 degrees to a vertical position for better viewing. A cord passage brings system pressure oil to the upper port on the solenoid valve body. The illustration shows the spool of the solenoid valve in its raised, activated position. Oil entering at the upper port is directed through the middle port of the valve to the back of the neutralizer spool. Oil flowing from the solenoid valve causes the neutralizer spool to move to the left against spring pressure. This blocks the supply of fill oil to the directional clutch pack and indexes the directional clutch pack oil supply passage to sump. With apply pressure oil blocked, the transmission responds as though it were in neutral. Note that the movement of the neutralizer spool cuts off the flow of oil to the directional spool regardless whether the directional spool is in the forward or reverse position. The disconnect solenoid valve consists of an electromagnetic coil, a ferrous metal plunger, and a control spool. The spool is slotted into the bottom of the plunger. The electrical circuit to the coil in the solenoid valve is completed whenever the left brake pedal is used to stop the machine. When the solenoid is activated, the electromagnetic coil will cause the plunger to move up, lifting the spool as shown in the illustration on the right. When the spool is in the raised position, a flow of oil at system pressure off a cord passage from the back of the main regulator spool is directed to the neutralizer spool as described in the previous frame. When the solenoid coil is deactivated, as shown in the illustration on the left, the solenoid plunger and valve spool move back down by the action of the spring located at the top of the plunger. In the lower position, oil flow used to actuate the neutralizer spool is cut off, but the passage to the neutralizer spool remains open so that the oil behind the neutralizer spool can drain to sump at the bottom of the solenoid valve spool. The neutralizer spool is returned to its position by the same spring that regulates torque converter return pressure. This spring maintains a 50 psi pressure on converter return oil during normal operation. When the neutralizer spool is shifted, torque converter return oil pressure rises to approximately 80 psi. The questions that follow will help you check your knowledge of the transmission disconnect circuit. Stop the tape while you are answering the questions. The answer to number 1 is C. The transmission disconnect circuit functions in both forward and reverse drive. The neutralizer spool cuts off apply pressure oil before it gets to the directional spool. This causes the engaged directional pack to disengage and interrupt the flow of power through the transmission. The answer to number 2 is also C. The left brake pedal places the transmission in neutral and stops the machine as well. The right brake pedal stops the machine but will not disengage the transmission. The answer to number 3 is A. The switch on the left brake pedal activates the transmission disconnect solenoid valve. The answer to number 4 is also A. The neutral start switch is located on the control valve at the directional spool. It detents to complete the circuit to the cranking motor only when the directional spool is in the neutral position. The electrical circuit remains open in forward and reverse, even when the transmission is disconnected by applying the left brake pedal. The remaining portion of the program is designed to help in the diagnosis of problems that might occur in the transmission and torque converter systems of the 510 and 515 payloaders. Problem diagnosis is a systematic process of elimination, starting with the obvious first and then working toward the more remote possibilities. A machine profile is helpful in problem diagnosis. One machine can differ from another and both be within specifications. A new machine should be tested when delivered. A record of initial pressure readings and engine stall speeds will help in interpreting readings taken at a time of trouble. Regular maintenance is one of the best ways to avoid problems in the operation of the payloader. A daily check of the machine may help locate problems such as loose or poorly aligned drivetrain components, dragging vehicle brakes, and so forth, that may otherwise be mistaken for torque converter or transmission system problems. The photo on the left shows the 2 sight gauges on the lower left side of the transmission. The oil must completely fill the lower sight gauge before the engine is started. The upper sight gauge is used to check the transmission oil level when the oil is hot. With the engine operating at low idle and the transmission in neutral, transmission oil should be approximately at the center of the upper gauge. Oil is added to the transmission through a filler tube located on the left side of the transmission. The photo on the right shows the cutout provided in the rear frame for viewing the transmission sight gauges. A low or high fluid level, incorrect oil viscosity, or a high water content in the oil can cause overheating and various other malfunctions to occur in the torque converter transmission system. If the oil shows signs of aeration, a suction leak or inefficient pump could be indicated. If the oil needs to be changed, both the pressure filter and the suction screen should be serviced. Contaminants found embedded in the filter elements can be helpful in determining the location of the failure. For instance, aluminum particles would indicate converter component wear. Steel particles could indicate pump or control valve failure. After performing preliminary inspections and observing the machine in operation, the serviceman should know if the problem affects one circuit or if the total system is affected. He should also know that individual components are included in the affected circuit and what is the proper functioning of each component. A sluggish response of the torque converter transmission system could be caused by an engine problem rather than by the malfunction of a component in the system. This is possible because the charging pump is driven off the engine flywheel through the impeller. For this reason, engine operation and efficiency cannot be overlooked when diagnosing a torque converter transmission system problem. To determine if the torque converter transmission charging pump is operating at its correct RPM under a load condition, a converter, a hydraulic, and a full stall speed check should be performed. A tachometer should be attached to the engine if the payloader is not already equipped with one. All systems should be at operating temperature throughout the test. The engine high idle setting must be within specifications before accurate results of the other tests can be achieved. The correct engine high idle setting is between 2600 and 2700 RPM on both the 510 and the 515. To perform a converter stall check, engage the transmission in third gear forward and apply the parking and right foot brake. Accelerate the engine to full throttle and read the maximum speed of the engine on the tachometer. A hydraulic stall check is performed in basically the same manner as the converter stall check, except that instead of engaging the transmission, the bucket circuit is energized in the rollback position. When the bucket cylinder is fully extended and maximum hydraulic pressure is achieved, read the engine speed on the tachometer. A full stall check is performed by engaging the transmission in third forward and rolling back the bucket while reading the maximum engine speed on the tachometer. In all cases, the stall check should not be run for more than 10 seconds at a time. For this reason, several readings should be taken for each check and the engine speeds averaged. The 510 and 515 rated stall speeds are shown on the illustration. The three stall checks are very informative to the serviceman when compared to each other. For example, if engine RPM drops below specifications for the full stall check, an engine problem is indicated. If the high idle RPM and the hydraulic stall check RPM readings are within specifications, and the converter and full stall check RPM readings are high, malfunction of the torque converter transmission charging pump might be suspected. Another possibility would be leakage in the converter, transmission, or control valve. All torque converter and transmission system pressure test ports are conveniently located on the face of the control valve assembly. The position of the major system test ports is shown in the photo. If the machine operates sluggishly in all gears and no engine problem was noted, a check of main, converter, and lube pressures will help pinpoint the location of the problem. The test port for checking main pressure is on the right side of the mounting flange for the inlet tube from the charging pump. It measures the pressure on the oil just upstream from the main regulator spool. Charging pump fluid flows internally past the main regulator spool to the torque converter. It then returns by an internal passageway to the converter regulator spool on the left side of the control valve. After overcoming spring tension on the converter regulator spool, converter return oil flows through an external hose to the cooler. The photo shows the converter pressure test port on the mounting flange for the outlet hose to the cooler. The converter test port measures return oil pressure just upstream from the converter regulator spool. The test port for checking lube pressure is located at the lower right corner of the control valve. It checks pressure on the oil returning from the cooler just before the oil is sent internally to deliver lubrication to the clutch packs. Main, converter, and lube pressures are checked first with the transmission in neutral. These three gauges should be left in place and observed again when checking clutch pack apply pressures. The location of the test ports used to check directional and range clutch pack apply pressures is also shown in the photo. Pressures are taken by removing the appropriate Allen plug and inserting the gauge hose with an elbow fitting. Tests are taken with the engine at high idle and with converter oil at operating temperature. The parking brake must be engaged and the safety bar must be in the lock position. This schematic shows the control valve with the transmission in neutral. The location of the test ports is indicated. Main pressure should be between 310 and 335 psi. Low main pressure will often be accompanied by low converter and low lube pressures. Low main pressure could be caused by a clogged suction filter, an inefficient charging pump, a weak 30 psi spring on the outside diameter of the regulator spool, a weak modulator spring, or a spool that is bound open, indexing a large quantity of charging oil to the sump. Excessive leakage at the dump spool or the modulator piston would also produce a low main pressure reading. Pump efficiency can be checked with a flow meter. The charging pump for the 710 transmission is rated at 20 GPM at 2,500 engine RPM. Converter outlet pressure has an operating range from 40 to 60 psi. At high idle, minimum operating pressure should be approximately 50 psi, whether the transmission is engaged or not. Initial cold oil startups will cause the pressure to reach a maximum of about 80 psi as the spool moves to the right against spring tension to allow the oil to drain off to the sump. Converter outlet pressure will also approach the 80 psi maximum whenever the neutralizer spool is activated, since it adds tension on the spring behind the converter regulator spool. A low converter outlet pressure, along with the normal main pressure reading, indicates converter leakage or a converter regulator spool stuck fully open. Both of these conditions would result in a low lube pressure reading. Converter leakage would reduce the oil supply before it reached the regulator valve. A valve that is bound in the open position would cause oil to drain to the sump instead of flowing onto the clutch packs for lube. A weak spring behind the converter regulator spool would cause a reduction of converter pressure at low idle. A broken spring would cause a sharp pressure drop and would also cause the neutralizer spool to remain activated after it was applied. A high converter outlet pressure would be an indication of a restricted cooler. This condition would produce a low lube reading since return oil is forced to drain to sump at the regulator valve because of the downstream restriction. Lube pressures will range from 5 to 8 psi at low idle. At high idle, a range of 12 to 15 psi should be observed. A short review on problem diagnosis follows. Stop the tape while you are answering the questions. The answer to number 1 is C. Transmission oil must be covering the lower sight glass before starting the engine. The answer for number 2 is B. A converter transmission problem is indicated if a good engine high idle reading is accompanied by a converter stall reading that is higher than specified. The answer to number 3 is B. Main pressure should read a minimum of 310 psi. The answer to number 4 is D. Converter outlet pressure reaches its maximum at all the conditions listed. In each case mentioned, the spring behind the converter regulator spool is at its highest compression. 4 temperature indicators are located on the instrument panel. The 2 at the top measure engine coolant temperature. The 2 at the bottom measure converter oil temperature. 2 separate switches are used for each system. One is a temperature-sensitive sending switch, which uses a variable resistance. Depending on the temperature felt, it sends a greater or lesser amount of current to the gauge on the instrument panel. The second switch is a bimetal on-off type switch. The contacts on the bimetal switch used for the converter close to complete the circuit to the system failure light when converter oil temperatures reach approximately 250 degrees Fahrenheit. A converter temperature problem should be checked out any time a gauge goes out of the green operating range, 176 degrees to 212 degrees Fahrenheit, instead of waiting for the system failure light to go on at 250 degrees Fahrenheit. Close observation of these gauges will enable the operator to discover a problem before it can cause serious damage to the system. If high engine coolant temperatures accompany high converter oil temperatures, an engine cooling system problem is indicated. A high converter temperature will often accompany a high engine temperature because of the fact that the oil cooler is located at the bottom of the engine coolant radiator and depends on engine coolant to dissipate its heat. High converter temperature is an indication of aerated or contaminated oil, a converter regulator spool not fully opening, or a restricted oil cooler. A low oil supply or converter leakage would show up immediately as a high temperature problem because of the heat produced by slippage and turbulence. Oil lost through leakage at the converter drains directly to the sump instead of going to the cooler where it would ordinarily lose its heat. Oil lost through leakage will reduce the lube supply, resulting in an increase in the heat of friction in the clutch pack shaft assemblies. This illustration shows the location of the clutch pack pressure test ports on the face of the control valve. It also shows the position of the directional and range control spools. The pressure test ports are positioned downstream from the control spools so that pressure is read in the circuit between the control spool and the engaged clutch pack. If trouble is found only in one direction of travel, a check of forward or reverse clutch pack pressure will be required. If trouble shows up in both directions but only one range, a test of first, second, or third speed apply pressures will be required. Clutch pack apply pressures should be no less than 10 psi below main pressure read at the same time. Pressure checks should be made at high idle with the safety bar in the straight lock position. The parking brake and the right foot brake should be used to hold the machine. If main pressure is normal and converter pressure is high and no movement is taking place in either direction, it is possible that the neutralizer spool is remaining in the applied position. This could result from the neutralizer spool being stuck in the applied position or the solenoid valve being stuck in the actuated position. The illustration shows the transmission in first speed forward with the neutralizer spool fully applied. If the spool remained in the applied position after the solenoid valve closed, both the forward and reverse test ports would continue to show a 0 pressure reading. A malfunction in the electrical circuit could also be the cause of a neutralizer problem. If the switch under the pad of the left brake pedal is stuck closed, the neutralizer spool will always remain applied. If the switch is not working at all, or if there's a broken wire or bad connection in the harness or solenoid coil, the solenoid plunger will not lift up. Under these conditions, pressure would not be cut off to the directional spool, and the transmission would not disconnect when the left brake pedal was depressed. With the ignition on, an audible clicking should be heard at the when the left brake pedal is depressed. If not, a volt-ohm meter can be used to isolate the location of the electrical problem. This illustration shows the directional clutch pack shaft engaged for forward drive. Apply pressure oil and lube oil is shown entering at the left to flow through drilled passages in the shaft. The lube pressure gauge should remain in place and be observed when clutch pack pressures are checked. If a low forward apply pressure is accompanied by a high lube pressure, a failure of the sealing ring on the shaft between the two supply ports is indicated. If a low forward apply pressure is accompanied by any pressure on the draining reverse oil supply line, failure of the sealing ring between the two apply pressure ports is indicated. If this sealing ring was leaking, reverse apply pressure would be low, and the draining forward drive supply line would show some pressure when the transmission was shifted to reverse. A leak at the sealing ring on the left side of the reverse port would show as a pressure loss in reverse, but would not produce any pressure reading in forward. If a low apply pressure reading on one gauge is not accompanied by a rise in pressure on either of the other two gauges, the leakage could be taking place across the sealing rings of the applied piston or in the internal delivery tubes. This same comparison of lube and apply pressures should be used if a sealing ring leak is suspected on the range clutch pack shafts. If a low apply pressure observed in first speed is accompanied by a high lube pressure, the sealing ring between the two ports must be replaced. If a low pressure observed in second or third speed is accompanied by a pressure rise on the lube gauge or on the gauge in the test port of the unapplied clutch pack, the shaft sealing ring is leaking and must be replaced. 4 sealing rings are used to separate the oil supplied to the annular grooves at the end of the directional clutch pack shaft. A few questions follow, which will check your knowledge of problem diagnosis in this area. Stop the tape while you are answering the questions. The answer to number 1 is C. If this sealing ring was leaking, forward apply pressure would be low and the lube reading would be higher than specified. The answer to number 2 is D. If lube pressure is low and both of the other pressures are normal, the only sealing ring that could be leaking is sealing ring D. The answer to number 3 is B. If both forward and reverse are affected, the sealing ring between the forward and reverse oil supply ports is the only one that could be the cause of the problem. This photo shows the converter housing removed from the transmission housing. The converter is not visible in the photo. It is installed on the back side of the housing. The stator assembly is spline mounted to the ground sleeve. The back portion of the ground sleeve is visible in the photo. The location of the control valve is on the right of the housing as shown in the photo. Apply pressure oil is delivered from the lowest part of the control valve through internally drilled passages in the housing to the carrier bore for the second and third speed clutch pack shaft. Lube oil is delivered through another drilled passage at this point. The lube flow then goes through a cord passage in the housing, as shown in the photo, up to the carrier bore for the first speed clutch pack shaft. The flow then goes through a tube to supply lube to the directional clutch pack shaft at the top of the housing. Apply pressure oil is delivered to the forward and reverse clutch packs through cord passages from the control valve and then through tubes, as shown in the photo, to the directional clutch pack shaft at the top of the housing. The retainer plate shown in the right center of the photo covers the converter inlet and outlet delivery passages. Oil going to the converter and to the directional shaft flows through passages in the ground sleeve before reaching its destination. If internal leakage is indicated, it might be between the ground sleeve and the converter housing. Leakage could also occur at any place where the tubing is fitted into the housing. If the gasket under the retainer plate was leaking, converter oil would be lost. If the transmission operates properly under load, but shifts too slowly or too rapidly, a modulation problem is indicated. The illustration shows the location of the test port provided to check modulation pressure buildup. It checks pressure on the fluid between the modulator piston and the dump piston. Pressure in this cavity should be no more than 30 psi below main pressure after the clutch packs have filled. Full modulation pressure should be reached in approximately 3 seconds for first speed, 2 seconds for second speed, and 1 second for third speed. If modulation takes place too rapidly, shift shock will result. Rapid modulation can be produced by an accumulator piston or a dump spool stuck in its bore. It can also be produced by a broken spring on the accumulator piston or the check valve stuck closed. As shown in the illustration, a pressure test port is available for checking accumulator operation. Pressure should drop to 0 momentarily each time a shift is made. A gauge without a snubber must be used to read this pressure. A slow modulation time can result from a restricted orifice. If all range selections engage slowly, the fill orifice, restrictor orifice, or timing orifice could be at fault. If modulation is slow in second or third speed, but normal in first, the trouble will be in the orifices supplying fill oil from the range spool to the modulation cavity. If the transmission has a low modulation pressure, all clutch packs will be slow to engage and might slip under load. A low modulation pressure would indicate a weak or broken spring behind the modulator piston, or leakage to sump because of a malfunctioning dump piston. A low modulation pressure cannot be mistaken for a low clutch pack pressure problem. A clutch pack pressure loss would affect only one range or one direction. A low modulation pressure would show as a low apply pressure in all ranges and directions. A low modulation pressure cannot be mistaken for an inefficient pump problem. An inefficient pump would result in low apply pressure in all selections, but it would also show up as low main pressure before engagement. This completes the program on the torque converter and transmission used in the 510 and 515 payloaders. A number of other programs have been produced by Marketing Services for the 510 and 515 payloader. They include a general machine orientation program and a customer maintenance program. Separate systems are covered by this program on the torque converter and transmission. Separate systems programs on brakes and axles and on steering and loader hydraulics are also